Hi, welcome back. So today I'm going to start a very important concept called change of variables. Or basically, how we are going to make use of the change of variable while performing integration. So before that, what I'd like to do, let's say what we did earlier. We talked about double integrals. So in double integrals, initially we were doing everything in your Cartesian coordinate system. So then we also, learned how to perform integration in polar coordinate system. So basically, you see that the only thing that we are worried about is this dA. Okay, and in polar coordinate system, you saw that this eventually it transformed into something like your f of r cos theta, r sin theta. Then dA it turned out to be r dr d theta. Okay, fine. And then in triple integrals, when we considered, symmetrical polar coordinates, again, because here what we were doing, we were thinking about, x, y, z system being transformed into r theta z. Okay, so basically z remains z, but r theta, that is nothing but what you do in 2 dimensions. You just simply convert some 2-dimensional planar region in xy coordinates into r theta coordinates. Okay, so that is what we are going to do. So now, if we talk about, spherical polar coordinates in 3D, spherical, I'll just quickly do a quick review of this. Probably you would have already learned, but still, I want to do a quick review because probably many of you, you simply just memorized it. So what we do here, say suppose I am considering this Cartesian coordinate system, and suppose I consider a point P x, y, z there. So what I do here, I imagine that this point P lies on a sphere of radius rho. Okay, so basically what happens, say I assume that since this lies on a sphere of radius rho, it is something like this. So this is rho. So then what I do, I draw a perpendicular from the point P to the xy plane, and then join the origin. But you remember these things that we are doing, so joining the origin to the foot of the perpendicular. This is extra. You will see why it is extra. So now let us assume that this radius it makes an angle phi with z axis. So then you will see that because I am considering this xy plane and I am considering this radius here. So my situation is something like this. Say, suppose this red pen, it is nothing but the z axis. So what is happening here? If the booklet that I'm holding, it is the xy plane. Then what is going to happen here? Oh my God! I need some helper here. Okay, anyway, don't worry about it. Say, suppose this pencil is the radius, radius vector. So then this is going to, I mean, make this is how you can rotate this radius vector. It is maximum, it is going to lie on the xy plane, and again from here again to the other side you can rotate it, or if this is the z axis, this is the radius vector, you will see that its extent is going to be from here to here, right? So that means it can traverse an angle. It can traverse an angle whose extent will be maximum pi. Okay, so now let us come back to this foot of the perpendicular, and then let us assume that this OL, it makes an angle theta with x-axis, theta with x-axis. So as before, what is happening out here? So if okay, fine. So then forget about this radius for the time being. Forget about this radius for the time being. So if I consider only the xy plane, so the coordinates of L is xy 0. So then you know that your x equal to your r cos theta and y equal to r sin theta. If what? If OL is r. Okay. So now if I consider this triangle OPL, so then this angle is 90 degree. And again, if you consider this angle, so I have a situation like this. So this is OPL. So this angle is going to be 5 by 2 minus 5. This one, I'm talking about this angle. Then OL, this is R. OL, this is R. Then OP, this is rho. OP, this is rho. So then you know that your R by rho, this is going to be cos pi by 2 minus 5, right? So this implies your R is going to be rho sin phi. Is it okay? So that is why your x, it eventually becomes rho sin phi cos theta, and y, it becomes rho sin phi sin theta. Okay? And then you know that PL is nothing but J. PL is nothing but J. So now J by rho is your sin pi by 2 minus 5. So that is cos phi. So that is why your J equal to your simply what? Cos phi. Rho cos phi, sorry. Is it okay? So this way we convert the Cartesian coordinate system into the spherical polar coordinate system. Okay. So now I would like to show you again some more visuals here. I would like to show you some more visuals here. Quickly, I will do. Please don't think that I am repeating a lot of stuff. The thing is that because you are going to see the video recording, it has given me the liberty to cover a lot of stuff, which otherwise I won't have covered in the class. I have told you simply to read it on your own. So this is about your spherical polar coordinate system. So this is the thing I have told you about. So if we assume that the point P lies on the surface of the sphere of radius rho, and if this radius vector makes an angle phi with z axis, and then we draw a perpendicular from P to xy plane. So this is P prime is the foot of the perpendicular. You join this, so this is R with this angle is theta. So then eventually this is my transformation. So now, and of course here, the equation of the sphere is going to be x squared plus y squared plus z squared equal to your phi squared. Okay. So now another thing is that, if I think about, and again, as I have told you, the if I consider a spherical wedge, I'll show you the spherical wedge just in the next slide. So then the limits of that wedge, limits of your rho, theta, and phi. See, you can see that it is between, rho is between A to B, theta is between, say, some alpha and beta, and alpha minus beta, it is 2 pi, because you know that in 2 dimension, whenever you consider the polar coordinate system, you will see that theta lies between 0 and 2 pi, and I have already explained how the extent of phi would be from 0 to pi, right? So this is the way they do. This is the spherical waves we are talking about. So this is very important. When you want to perform triple integration by considering the spherical polar coordinates, kind of uniquely. Okay. So I just don't want to go into detail of all this stuff. Please don't think that I am avoiding them. I am simply ignoring them because I am going to bring everything under the same umbrella. Okay, so that is what we are going to do. Like say you are going to perform integration like this in a unit ball. Here you see that region of integration is given to be a unit ball. And again, in my next figure, you will see that I'm going to perform integration. I'm going to perform integration of some function. Basically, it is telling me to find out the volume. So I'm simply going to integrate 1 fx x y j equal to 1, and you will see that now you look at the shape of this region. This is nothing but, this looks like what? Can you tell me what does it look like?
Ice cream cone.
Yes, it is exactly. It is the ice cream cone. Okay, so you know that this is going to help you in finding the volume of an ice cream cone as well. So we are going to deal with integration like this. We are going to deal with integration like these also, right? But we are not going to go in the longer route way. So what we are going to do is see change of variable in multiple integrals. So I would like to bring everything under one umbrella, which is going to make your life, to be precise, mathematical life, to be precise, your calculus life, multivariable calculus life, much simpler. Okay, so this is what we are going to do. So now I'm going to move to this change of variables in multiple integrals. Okay, so what is this change of variable in multiple integrals? Okay, so now change of variable, COV. Of course, it is not COVID. Don't worry. So change of variable. Say suppose if we consider it for single variable calculus. Suppose I consider this definite integral. So then you know that if again I consider x to be some function of another variable u, right? So then what I would have done? Initially I would have considered this integration in this interval, right? So then this is going to be transformed into some another interval Ct in such a way that your A equal to Z of Z and B equal to Z of D, right? And this should have transformed into CD f of GU G prime U DU, right? And of course, I would have simply written this as a function of this. So then, I mean, you have simply written it as f of x of u, and then this would have been dx du t. Okay. So likewise, what we are going to do in double integral, what we are going to do, we will going to make change of variables like say uv to xy, change of variables from uv to xy, and here say the function I have taken as g, right? So similarly, it is going to be defined by some transformation, by some transformation of this. Okay, so this transformation is nothing but a mapping whose both domains and codomains, they are subsets in R2. Okay, so how this is going to work out? So basically, what is going to happen? I am going to consider some function like x equal to g of uv and y equal to say h of uv. Okay, right? And then what it is going to do, like say suppose this is your uv plane, and I have a region here. I have a region here. Say suppose this is your S, and this is going to transform into some region R under the transformation T. This is going to be in xy plane. Okay. So if I take any point, say E0, V0, okay, and then its image here is going to be x0, y0 under this transformation. Okay. So now, if this mapping T is 1, 1 and onto, you know the meaning of 1, 1 and onto. Okay. So then what is going to happen? The inverse mapping from this domain R to this domain S. Of course, this domain belongs to xy plane. Now this domain S belongs to uv plane. Okay, so that is possible. Okay, so now firstly let us take one small example how this works out, and after that I will go to the actual multiple integration part. Okay, fine. So let us simply think about. So then here if this inverse transformation exists, so then earlier we had this under the transformation T. So then under the transformation T inverse, what I can get? I can get say U to be some function of capital G of xy and V to be some function of capital H of xy. Okay, so I will just take one small example which is going to illustrate what we are trying to do. This is what it is. Okay, let me take a small example. Suppose a transformation is defined by these equations: x equal to u squared minus v squared, and your y equal to 2uv, right? So then what you have to do, you have to find the range of the square s defined in uv simply as this. Okay, so basically what we are going to do, we are going to find out the image. Of this square S from UV plane to the xy plane. In the xy plane, we are going to find it out. Okay, so now this is UV plan. This is UV plan. Okay, fine. This is UV plan, and then you know that this is 1 0, then 1 1 0 1. Okay. So the first thing here is that what we will do, we will try to see here this square. It has boundaries. Say this S1, S2, S3, and S4. Okay. So if this mapping is 1 1 and on 2, then each point of this domain is going to map onto only one point in another region here. Okay, fine. And likewise, the inverse transformation also we will be able to define. So now what is going to happen? One thing you should remember: the boundaries here in this plan is going to transform into boundaries here in this XY plan. Okay, so that is why if we can find out the boundaries of the image of this domain in XY plan, then everything is going to be straightforward. So you'll be able to find out the region, which is enclosed by that boundaries. Okay, fine. So, okay. So now here you can see that how is S1 defined? S1 here what? Your V equal to 0, right? And U goes from 0 to 1. Okay? And S2 here U equal to 1.
1.
Yes. And V goes from
0 to 1.
0 to 1. And then S3 here you can see that V equal to 1. And again U goes from 0 to 1. And S4 what is happening out here? U equal to 0. And of course V goes from 0 to 1. Okay. So now let us consider their respective images. Let me call it simply S1 bar in XY plan. Okay. So what are the transformations? So here your V equal to 0. See here V equal to 0. So obviously I am simply going to have x to be equal to u square and y to be equal to 0. Is it okay? Fine. So then what is going to happen? Then what is going to happen here? So you have found out x to be equal to u square. So now you can see that u goes from 0 to 1, right? So that is why this x is also going to go from 0 to 1. Is it okay? Because x is equal to u square. So that means here S1 bar is simply going to be your x going from 0 to 1, y equal to 0. Fine. So this is my S1 bar. Okay. So now let us come to S2 bar, which is the image of S2 here. So here u equal to 1. So my x is going to be 1 minus v square, and then your y is going to be 2v, right? So that means your v is going to be y by 2. So that is why this is going to be 1 minus y square by 4. 1 minus y square by 4. Okay. So now if you recall here, your v was going from 0 to 1. Right? So that means y is going to go from 0 to 2. Isn't it? Right? So basically, we have to simply draw this graph for this one. Is it okay? Fine. So
Yeah.
now I'll simply teach you some trick how to draw this kind of graphs. It is very straightforward. You don't have to even use tabular form or something like that. Okay, fine. See, I'll just give you a quick rough idea about how to go about it. So suppose this is X, this is Y. So one, then say this is good enough for me. Okay. Say this is the graph. This is the graph. Your X equal to Y square. Is it okay? Fine. This is the graph. This is the graph X equal to Y square. Okay. So now, if you want to have X equal to Y square by 4, X equal to Y square by 4. Now, say suppose I want to draw Y square by 4. That is going to be more steeper, isn't it? Because now say what this is 1, 1. Okay. So now, what is going to happen when your Y equal to 1, X is going to be equal to 1 by 4, isn't it? So I am going to have
When Y equal to 1, X equal to 1 minus 1 by 4.
No. That I'll come later on.
Oh, this is Y square.
I am simply trying to draw the graph of X equal to Y square by 4. Okay?
Okay.
Fine. So this is my graph. And then you will see that when Y equal to 2, X equal to 1, isn't it? Y equal to 2, X equal to 1. So this is 1, this is 2. So I'm going to have a graph like this. Okay, fine. So that means my minus y square will be given by something like this, right? Where this is 2. Minus 2, sorry. This is minus 2.
Yeah.
Right? So then what I will have to do? If I want to find out 1 minus y square by 4, I'll have to simply raise this graph by 1. Isn't it?
Yeah.
Fine?
Yeah.
Just I minus y square. So eventually what it is going to look like, we will see that here, if this is 2, eventually it is going to look like something like this here. Okay, it is going to look like something like this. So this is going to be your 1 minus y square by 4. So likewise, you'll be able to see that this S3, this is 1, this is minus 1. Again, S3 is going to be this. That is going to be because your just a minute. Here it is going to be u square minus 1. U square minus 1. So this is eventually going to be y square by 4 minus 1. This is x equal to this. This is okay. And eventually this one is going to be your S4 bar. This is S2 bar, S3 bar, and so on. And so this is going to be your domain. So if this is S, this is R. So under this transformation given by those two formulas, this is transformed into this. Okay. So this is the way it is going to work. So see, one thing I would like to mention is that. So now see, I have taken a mapping from UV plane to XY plane. But in reality, what I will be interested in later on, you are going to see that I will be interested in the mapping from XY plane to UV plane. Okay, I'll take certain examples, then it will be more clear to you. So now let us come to the actual change of variables. I mean, how we are going to perform integration. So now I will come to that point. Okay. So how change of variable affects your double integrate. So let us come to that. Okay, so variables affect your double integrate. So let us try this. Let's try how this happens. Okay. So again, what I'm going to do, say suppose this is UV plan, okay, and we are considering a very small. In fact, this is an elementary, I mean, rectangular domain here. Okay, so let us assume that this point is U naught V naught here, U naught V naught here, and suppose this length is delta U, and this length is delta V, right? So basically, this point is your U naught plus delta U V naught, and this point is U naught V naught comma delta. Okay. So now we are interested in the image of this region, say maybe S, and then in XY plan, suppose this transform into something like this. This is X, this is Y, and suppose this is the image of U naught V naught onto the XY plan. Okay, fine. So what I may assume that, so maybe as before, I can assume X it to be a function of UV, right? And Y to be a function of UV. Fine? You have already seen how it affects. Like earlier we had seen that X equal to U square minus V square, Y equal to 2UV. It is something like that. Is it okay? Fine? So now let us move to this. I mean, these domains. Say, let me call it as R. Say, let me call it as R. Call it as R. So now, let a general point here. Say, suppose this is UV. Okay. So if it transformed into a point, say x1, point xy. So then, what I can do? I can, like, say this point xy. So if it is p, so I can denote it by a vector r. So that r in xy plan, it is simply going to be xik y j. Right? Up to this is clear. Or I mean, if in terms of transformation I want to write j, so basically what it is going to be x UV I plus Y UV J. It is, I can write it something like this. So far so good, right? Is it okay?
Yeah.
Yes, sir.
Fine. So now one thing, I have already told you that boundaries correspond to boundaries. Okay. So now if I consider these two boundaries, so they are going to transform onto these two boundaries, isn't it? Right? Now you will see this boundary, which is a curve, I mean line in XY plan, how this is defined. So here for this boundary, your V was constant, isn't it? Is it okay?
Yeah.
Yes, sir.
side. So any vector, say suppose any vector here, if I consider any vector, so that means any vector here, that is going to be denoted by u v naught. It is going to be something like this. Fine. Okay. So far so good, right?
Yeah.
Now let us concentrate on this curve. So this is simply R u v naught. Any point on this curve, can be described by this vector R u v naught, right? So now, if you recall what we did earlier, say if I consider a plane curve, you take any point here, So then this R, it can be described in terms of the parameter t. This is xti plus ytz. It is something like this. Is it okay if I express x as a function of t, y as a function of t? If the coordinate of this point is then xt comma yt, so then I can define this vector. I can define this curve by this vector rt. Fine? Is it okay? Yes?
Yes.
So now look, since v naught is fixed here, so this curve has a parametric representation in terms of the single parameter u. Yes? Fine? Okay? So
Yeah.
since it has been parameterized by a single parameter u, so now you know that if you want to draw a tangent to this curve, at this point, that would have been simply r prime t. Right?
Yes.
Similarly, if I want to consider a tangent here, that would be given by the derivative of r with respect to the variable u at that point. Clear?
Yes. Yes, sir.
Isn't it? Fine. So that is why if I want to consider a tangent to this curve at the point x naught y naught, that would be simply what? So that means here derivatives mean partial derivative, isn't it? So partial derivative, because this is a function of u and v, original function, right? So I have to take the partial derivative with respect to u here, right? In order to find out the tangent at any point lying on this curve. So if that point is this corner point, so that means a tangent to this corner point x naught y naught, here it would be simply given by r u naught v naught. Is it okay?
Yeah.
Fine. Similarly, if I want to consider a tangent at this point along this boundary, that would be given by your RV u naught v naught. Fine. So far so good. So this is the only thing. I mean that was the only difficult part in understanding this change of variable concept. You will see that the remaining part, it is going to flow. It is going to flow like water. Okay, it's going to be very easy. Okay, so fine. So let us see how to do that. So still say this, I have given you only a kind of micro picture. The overall picture will come later on. I'll just going to run through slides. Okay, once you learn this concept, then everything will be clear to you. Okay, see, next what I would like to do, I would simply like to approximate the area of this curved rectangle. Okay, that is what I'm going to do. So now you will see calculus is so beautiful. Like you will see how easily that area is going to be expressed. Okay, fine. So let these two figures still remain, or maybe since you have understood it, I can one figure maybe at that. Okay, fine. I'm still now XY plane, and then okay. See now, if I want to find out the area of this triangle, sorry, not this triangle, this curved rectangle. Okay, of course, this is x naught, y naught. Okay, say suppose I suppose this vector, this vector is a bar, and this vector, this is b bar. Okay, and you know that your what I can do here, just a minute. Okay, fine. So just okay. So then let us consider this vector and this vector, joining these corner points. Okay, so then you know that this vector is simply r u naught v naught, right? Is it okay? Fine. And then your this vector is going to be r u naught plus delta u v naught, because if you recall what I had this is u naught v naught, this is u naught plus delta u v naught, isn't it? This point. Okay, and image of this point was this, and image of this point was this. Is it clear?
Yeah.
Yes. So that means now look at this situation. Now this vector a, so it is simply nothing but the difference between r u naught delta u v naught minus u naught v naught, isn't it? Fine. Similarly, this vector, b, this vector b, it is nothing but this point was what? R u naught v naught plus delta v, right? Right. So b is going to be given by u naught v naught plus delta v minus r u naught v naught. Clear? So far so good, right? Okay. So now see, if I want to approximate the area of this curved rectangle, I can approximate it with the area of the parallelogram whose sides are a and b. Sides are given by the vectors a and b, isn't it? Yes. Fine?
Yes.
If you consider that to be a very small curved rectangle. Okay, so now basically I would be interested in finding this mod of a cross b. You know that this is nothing but the area of the parallelogram whose sides are given by the vectors a and b. Now let us look at the interesting situation. What is happening out here? How calculus is going to come to your rescue now. Okay, now look at this. What is this? This is simply limit delta u tends to 0, delta u r u naught plus delta u, or maybe fine. From the definition of partial derivative. So this implies your r u naught plus delta u v naught minus r u naught v naught. This is approximately equal to r u delta u, isn't it?
Yeah.
Fine. And what is this? This is simply the vector A. Of course, I am taking it at the point u naught v naught. Yes, right? Likewise, I am going to have V is RV delta V. Right?
Yes.
So now, so that means your A cross B, that is going to be RE cross RV delta U delta V. Okay, now let me come to RU cross RV. Okay, see my what RUB, that was what XUBI plus Y UBJ, isn't it? So therefore, your RU, this is simply going to be del X del UI plus del Y del UJ. So similarly, RV, this is going to be del X del VI plus del Y del VJ, right? And so that means RU cross RV, that is simply going to be IJK. So del X del U, del Y del U, 0, del X del V, del Y del V, 0, and you will see that this is simply equal to del X del U, del Y del U, del X del V, del Y. Is it visible? Yes. Del Y del V into K. Fine. So now, what I will do. So this determinant. I mean, many of you may not have come across this. So this is nothing but the Jacobian of the transformation. Given by your x equal to x UV and y equal to y UV, right? And that is denoted by your del xy del UV, and this is simply this determinant. So basically it is del x del u, your del y del v minus del x del v del y del e. Okay, so this is called the Jacobian of the transformation given by this. Okay, and so that is why this is simply del xy. I mean, because this is mod. Okay, so if you take the mod of this, so then I mean, because k is a unit vector, right? Mod of k is going to give you 1. So eventually you are going to come up with this. Up to this, everything is fine, right? Okay. So now let us run through these slides. What exactly we are trying to do here? what exactly we are trying to do here. Because you already know how to, perform integration. From the definition of, double integrate. So what we do, if we consider a domain, so then what we do, we subdivide the domain, right? If it is a rectangular domain, into some subrectangle, right? And if it is a curved domain also, we can consider into some sub-regions there. And over each region, what we can do, we can perform integration, right? And in order to perform integration, so what we simply do, we think about the volume of the column, right? And column is created by the region lying below the surface defined by the function f of xy, which is to be integrated, right? So now I'm absolutely sure that if now I simply run through these slides, you will understand all the concepts, okay? So let us do that. So this example we have already done, okay? So now let us see how a change of variable affects a double integral. So we start with a small rectangle S in UV plane, whose lower left corner is the point U0 V0. You have already seen, and then the dimensions of this rectangle is delta U and delta V. And suppose it has been mapped through the transformation T on xy plane by this cover rectangle R. Okay, so these concepts I have already explained to you, right? How this A becomes delta U. They are calling it TU. Sorry, not TU. RU said that is fine. All of a sudden it simply looks like TU. Okay. Anyway, so this is what it is, and this I have already explained all these concepts. Okay. So then you have seen that this turns into this. So RU cross RV, it is this. And this is the definition of Jacobian of the transformation T given by x equal to g of UV and y equal to h of UV. This is simply this. Okay, fine. So now let us come to this. Okay. So with this notation, now what we can do? We can use your this equation. We can use this equation. You know that. What is this equation? It was trying to approximate the area of the curved rectangle with the area of the parallelogram whose sides were given by what? A and B, right? So this is what it is. So then suppose I consider suppose this region S, it is mapped onto this region R in xy plane. Now, if I want to perform integration on this xy plane, so then what I'm going to do? I'm going to subdivide this domain R by curves parallel to the boundaries, okay, and that is going to generate a very small elementary curved rectangle like this, okay. And if this area of this curved rectangle is delta A, so it is approximately equal to the value this, okay. I have done one slight mistake there. So see, the mod sign will be still there. So I think the mod sign I missed, because if you recall, the area, it is simply mod of A cross B. So that is why the mod sign will be still there. Even if the determinant turns out to be, final value of the determinant turns out to be negative, you have to take only the positive value. Okay? And this Jacobian has to be evaluated at E non V now. So now, if we divide, say, S in the UV plane into rectangle Sij and call their images in the XY plane as Rij. That is what they have done. I told you about simply subdividing it by some curves parallel to the boundary, but that will be somewhat equivalent to if you just divide it into subrectangles by vertical and horizontal line, and you take their images on xy plane, you are going to get the same situation. So if you apply this approximation to each of those curved subrectangle Rij, So then we approximate the double integral of f over r as this. So you know this. So this is simply this one, and if you get limit m tends to infinity, eventually this is going to be this, and that is what happens. So the double sum is a Riemann sum for this integral. So that is where the change of variables in a double integral formula leads us to. Okay, am I still audible?
Yes, yes.
Okay, okay. Sometimes I almost think that I'm addressing to an empty room. Okay, anyway, so this is, and of course, this I forgot. T is a C1 transformation. So that means, continuous partial derivative of those functions which define the transformation, it exists. So, whose Jacobian is non-zero. In fact, let me tell you why this Jacobian is non-zero. Because this, Jacobian being non-zero, it guarantees you the existence of the inverse transformation. So that means if the Jacobian is non-zero, so we can say that the transformation which we define, that is going to be 1, 1 and on 2 or bijective. Okay, so that maps the region S in the UV plane onto a region R in XY plane, and suppose F is continuous in R, and that R and S are of type 1 or type 2 plane regions, and suppose also that T is 1, 1, except perhaps on the boundary of S. This in one example I'll give I'll show you some glimpse of it. Why they say except perhaps on the boundary of S. No? I'll tell you about this. Okay. So then the double integral of f over the region R, it is simply, it transforms into double integral of f over the region S, where you have to loop in the Jacobian. Okay, fine. So this is what it is. So maybe I'll just I'll just show you one example. So here, basically what you have to concentrate on, whenever you consider a change of variables, that Jacobian, mod of the Jacobian is very, very important. That is where our concentration will be. So I will quickly go through. See now here, and remember the polar coordinate system that we were taking. See that curved region, you are going to find out that in XY plane. Remember, this region, this polar subrectangle, if I take in your XY plane, where we have changed the Cartesian coordinate into polar coordinate system. So this becomes my situation where the R lies between A and B, and theta lies between alpha and beta. So, in fact, what is happening here? You have the original R theta plane, where we were considering a rectangular region, whose extents were given by your, R from A to B. So in this interval, see along, this is nothing but this R line, this is the theta line. Along the theta line, theta lies between alpha and beta. So this region S is mapped onto the region S here. So this is the polar subrectangle. So here, if I want change of variable, basically what I have to do, I already know that x equal to r cos theta and y equal to r sin theta. So for those two transformation, I have to find out the Jacobian of the transformation, and which is pretty straightforward. So this is the thing. You will see that it's pretty straightforward. Jacobian of the transformation will turn out to be R. Okay. So then, from the definition of the change of variables for a double integral, it will simply transform into this, and you will see that that is why we have R dr d theta. Okay. So this R comes from there. Okay. So I think with that note, I'm going to end today's class. So in my next class, I'm going to perform some integration for some examples, and then I would like to come back to your this spherical polar coordinate system. Okay. So till then, so some examples will be there. You can see here glimpse of that. And till then, I will meet you in my next class.